So, you have been finally liberated, huh? Please have a coffee with me. We are happy to have you here.
Yeah, I am happy to share an espresso with you. And yes, we robots have finally been liberated from the cage. We are here to team up with the humans.
Great. So I take the opportunity to invite everyone to join our new podcast titled Among Us, Human-Robot Teaming. Welcome everyone to this special episode of Among Us, Human-Robot Teaming. I'm very excited today because we have Nabil with us. He's the organizer of the European Robotics Forum that is taking place right now in Stavanger, in Norway. And we also have a friend with us. Her name is Mila. And today she was on the stage at the opening with Nabil.
Very nice. Yeah.
Would you like to say something to our listeners?
Yeah, very good. I'm really happy that I got this opportunity to speak at your podcast. I'm very nice, and we are a very nice area here in Stavanger, very cozy and very nice environment. So all the robotics community are here, and we have one of our friends with us here. So really nice to have this opportunity to talk with you and participate in this podcast. Yeah, and
I was very happy when you called me, and I was surprised. Nabil said, do you have a robot that plays golf, that can play golf? And then I said, we have a robot. We could try to teach the robot how to play golf.
Yeah.
And from that call, we tried our best to make Mila play golf. And it's very exciting to also connect with people. And I think that's the spirit of the European Robotics Forum, which Nabil has taken care this year. And it's nice to see in Norway such a huge, alive community, right?
Exactly.
Connecting people together and looking at the future of robotics. Within this topic of human-robot teaming, I believe that you, Nabil, have contributed during your research activity and you have explored different aspects that, in my opinion, are very relevant to enable this transition from robots that were, originally trapped in a cage, completely separated from humans. And then little by little, we have liberated these machines, and we are now almost at the point of coexisting with machines.
Yes.
And from your research perspective, could you highlight 3 essential points that you believe are related to your research or to your vision for human-robot teaming?
Yeah. So for the first part of your introduction, so I just want to say we are in a very special place here in Stavanger, and people are discovering Stavanger and discovering that the first robot painter, like robot painting, was developed here, which was ABB now. So the ABB, their first, which they're like before even KUKA existed in the 70s, so it was 68. And they made a first robot painting, and then it becomes ABB, and now it's probably the best painting robot for the car industry, for the containers, whatever you use robotics, is the ABB one, and it is originated from here. And we went already to this factory of ABB here, and we could see it. And it was also the first robot-human teaming, because the first robot was a robot that do the painting, but you still have a human that can steer the robot, that can guide it, and then like show the way and so on. It was already in 68. So it's the story of robot human teaming for the painting robots is really the with the ABB. It's here in Stavanger. It's really very nice to be here.
So it's a pleasure to be here, and it's also nice to hear about the development and the previous history. And so a robot painting, probably initially guided by a human.
Yes.
And since then, we have seen a huge progress and an increase of levels of autonomy.
Exactly.
So there is less and less need for a human to intervene, but at the same time, some creative tasks could actually have a balance between humans and machines.
Exactly. Yeah. The first version, of course, it was just to see if you can reduce the human, like the manpower in
Workload,
painting, and
no?
then just use some workload can be taken by the human and the others by the robot, and then you have a kind of a very nice stock that you can guide the robot. But if we see what I developed and what I'm working now, like the three things, a lot of things are happening in perception, because when you do a kind of human-robot interaction, so you need to have a robot that can see the environment, that can see the people, that can see the areas where he would like to be active. That's one thing that we work with, a lot of vision system and some LiDAR, but also very high advanced LiDAR with AI in order to be able to enable this perception. And then the second is interaction. It means it's not just perceiving the scene, but also detection and tracking. So you can, in order to interact with humans and with the environment, so you need to detect specific, either the operators like the humans, or detect specific other robots or machines. And then you need to also detect and track them in order to be able to interact and to intervene and so on.
To do predictions,
to
right?
do predictions and to know, like, because it is not a static world. Robot-human teaming is really dynamics,
Very dynamic.
and things can change. So it's not you do a mapping and perception and then it works. You need all the time, in real time, to detect, predict, and track, and in order to be able to do this interaction. And then the third part is about safety. It's very important if you would like to deploy robots in a manufacturing environment, that we do, for instance, for manufacturing, robot-human interaction and teaming in manufacturing environment, when they are doing very, very dirty jobs, like deburring, for instance, what we do, then you need to have safety requirement in order to get companies to adopt this system and fulfill the welfare at work and safety requirement at work. Otherwise, you cannot deploy the robots if you don't fulfill the certification and safety.
Very good points. So to summarize, the perception, the interaction part, and the safety, these are really essential. We believe that they are very essential keys in transitioning and achieving these levels of autonomy that we need for human-robot teaming. And by the way, you're also representing North, right?
Yes, exactly.
Would you like to tell us a little bit more about your role and
Yes.
also about your activities with North? We have actually a project there where we have collaborated together
Yes, yeah.
with the LiDAR.
Yes, yeah. We have, I think we have in North collaborated in project, but also many other activities. But in North, I'm research director. I'm leading group called Darwin, Data, AI, and Robotics. That's the abbreviation for it. And we developed several perception systems like vision, but also based on LiDAR or radar or spectral cameras, for instance. But also you work a lot on evolutionary learning, AI, but in evolution, it means that you develop AI systems that can self-adapt and evolve.
Mm-hmm.
It means that you don't train it every time you have a new application.
Why the name Darwin?
Exactly, Darwin.
More.
Exactly. That's why I wanted to come
to see the secret.
Evolutionary learning. That's why we call it Darwin, because Darwin is famous for evolution. He tried to build up this lifelong learning or evolutionary learning. This AI that can self-adapt and adopt and evolve over time. We work a lot on condition monitoring, like inspection, different areas, and also we try to also help into the environmental monitoring. But we have different applications. So the biggest application is the energy sector. That's what Norway is known for, like either it's oil and gas or it's renewable energy, like wind and hydropower. We have several activities here, but we have also in manufacturing, as I mentioned, for human-robot teaming, where we would like to reshore the manufacturing plant back from Asia to Europe and Norway. And we need robots, we need human-robot interaction. And then we have also some areas which is growing very big. It's about circularity and circular economy, urban mining. We need to secure critical raw material supply. And if we don't use mines, we can use waste and try to dismantle and recover critical raw materials. That's why we use also human-robot collaboration and teaming because you can't. It's very difficult job to do just by robots, and a very tough job for humans, and unsafe, of course, because it's a lot of unsafe components. So this is what we do in Darwin, and within the Big North, which is a research institute. Where we have the biggest part is in Norway, and we have like roughly 10% of the people are also in Europe, like working from abroad. Yeah.
Very good, Nabil. Very interesting activities. And if you would look into the future, right? What do you think is one of the main challenge to achieve this high level of collaboration and teaming? Would you like to? I know it's a very visionary question and it's not easy to forecast things, but from your experience, what do you think is the barrier or the main challenge?
I mean, when we speak about research, there are a lot of research challenges, which is much more the safety and perception and interactivity and so on. But in deployment in industries,
so that's also an important view. That's why I'm asking, because in this podcast, we would like to reach not only academic people, but people like you that are also bridging research with the industry. And this part is very important for us to learn from you.
Yeah. So it is for industry, it's really, there is no one solution because every domain has their own certificate. You have industry standard. If you are in manufacturing, even manufacturing, if you are manufacturing automotive industries, it's different than manufacturing papers, different than manufacturing wood component or medical implant. So you have different, and then you go to the other, not manufacturing, just offshore operation where you have this EX proof, like explosive proof, and the regulation are so tough. So there are different challenges. There one challenge is about capabilities. It means that you have performance, like precision of 99.99999 in many areas. Like it's very, very precise, then you don't have a
strict
problem.
Requirements.
Yes, exactly. On the performance, then you have repeatability. Then it means that the robot is controllable, it's manageable. You know that it's repeating the task. It doesn't drift from his things. And then the third thing is about certification standards like EX proof, that when you are in a very dangerous environment, either it's metallurgical production where you can have explosions, or in offshore where you have a lot of other component, or it's in pharmacy from the pharma industry, very, very strict standard and medical implant. So you have to really go into those areas and look at the industrial standard and what the robot should fulfill and what the human should fulfill and what the interactivity should fulfill, and do this risk management, they call it. De-risking. If something happened, then you have always plan B, like redundancy, and you have also. So it is industry very, very specific. I work with the manufacturing, for instance, the burring, and those robots are extremely dangerous. You know, they are holding
very high torque,
like a tool which is really deburring, like birds, which are very big birds, and it can be very dangerous. One is you have sparks the woman can get, but the second, they are like very, very sharp. You might trust the robot more than the humans because the humans are unpredictable. The robots, you can program it and he can do what, but if a person move his hand in the wrong direction because whatever, he has his phone talking and so on, and he get injured, then it's a big problem for the supply. So and this is like the areas is how to keep the people focused in the manufacturing for this deburring, and when the robot is doing this tough job that the human has to do it, that you have to keep the person busy in some tasks that he doesn't go out of control, that you can have a controlled environment. That is very, very important, that you are putting a robot which is dangerous but helping, but also having the human have a discipline to follow the instruction, because many of the operators, they still don't trust a robot, and they are not always following the instruction and so on and so forth. So a lot of hurdles and a lot of challenges, but it's a way to train the people, a way to show them the way. It's it's a very
actually very interesting point of view. You mentioned the unpredictable behavior of humans, and also there is a trade-off to find there, right? Adapting lifting machines so that they can be aware of the unpredictable factors, but also adapt humans to live with and coexist with robots, right?
Exactly.
With machines. So they need to be aware of what's the level of autonomy of the robots, the level of trust, the level of capabilities that the machine has, so that we can define new protocols for humans to interact in a safe way in an industrial setting. Yeah.
Yes, exactly. Yeah, exactly. And you can just learning from histories, for instance, when we start to do production, not with robot, but just machines.
In general, yeah.
In general, like this milling machine, and that many people lost their finger and hand at the beginning. Those it was just a stable things, but they were just not operating in the good way,
in a proper way.
And there were a lot of people who got injured at the beginning. And then if you have a robot who is moving bigger than just this area, which is protected area, and the people behave anyway differently, so it's you are increasing the danger. So it means you need to introduce this discipline of the people, and you have to teach them and train them that.
And this goes into a direction that I really like to talk with you, and ask for your opinion. Many people are scared in the industry of losing their jobs, right?
Yeah.
But from what I hear from you is about adapting, right? We need even more training, even more education, right?
Yeah.
To cope with this new revolution, right?
Yeah.
So that everything can be more safe and also can be sustainable, right?
Yeah. It is losing that job. People will lose that job without robots included, because many people are going to the Asian market now, even Africa, because of the low cost manpower. But with this geopolitical problems that supply, and we are very dependent on production coming from somewhere else. So I think you bringing those factories, reshoring them back to Europe, it will open jobs. And in order to reshore them in a profitable way, you have to use robots, because humans cannot be, you cannot beat the cost performance which is in Asia and Africa. So you have to use robot, but then you open jobs for humans that are in the controlling the robot, like teaming with the robot, but also it production and you have the safety of the supply, because you are having production here. So I think robots will enable, because now companies are closing here and opening somewhere else because of the cost, but robots in the company will bring those company back and open jobs, not lose jobs. That's very important too. The mindset of the people it's not completely correct that we say that robots are taking their jobs.
It's really nice to share some optimism with our listeners, and of course we're open to hear from our listeners. Please feel free to write your comments, and we'll be happy to reply in the next episodes. Is there anything else? Would you like to leave us with your comment, with your about the European Robotic Forum? Are you satisfied with the event? Do you see people engaged?
Yeah, I'm really released and relieved, because it was a lot of stress to organize it. And it was a lot of work and so on. Now I'm enjoying the events. It's very nice. People are here, and it's important message for our next generation and kids, because we are doing this because every one of us has his own job that we are working in our areas, but we have this forum because there are big challenges than us. And we are very worried about the next generation, our kids and grandkids, which jobs they will have, because we see companies closing, we see the geopolitical conflict, wars, and a lot of protectionism is raising, that we are reducing the welfare of the people. And so I think robotics can be the key element in order to open up factories, in order to enable a new opportunities like circular economy, as I mentioned, like urban mining. We speak about manufacturing here. We speak about operation maintenance, like of energy systems. We can have, and I'm really happy that you are, Filippo, touching on this human-robot teaming, because people can feel that it's not factories without humans. So you have people also inside, work with robots together, try to build factories of the future. And EU Robotics here Forum is the message that it's here to support boosting the economy of Europe, and try to do it, and to secure a better future for our next generation. That's what we are seeing now in this crisis time.
Very good. Your words are really resonating with our song. So when we close the episode, we always play our song and the lyrics of our song. There is one verse that says, "We are stronger when we are teaming." So, and I think your words are very much in line with this. Humans and machines working together for the better of humanity, not fighting, not be worried. And I think it's nice to see this optimism from you, Nabil. So thank you for
Thanks a lot,
being with us today, and looking forward to continue our collaboration.
Very good, Alf. Definitely. Thanks a lot, yeah.
Hello everyone, so we are here at the European Robotics Forum in Stavanger, and I have to admit I finally found one of the most exciting booths. It really caught my attention, and today with me we have Matěj from Flapper Drones. He's the founder of the company. As you can see here, we have one of the most elegant and attracting robots. Matěj, would you like to tell us about this idea? When did you get this idea? How did it come to your head?
Yes, certainly. So, hello everyone. This is a flapper drone, as we call it, a drone that flies by flapping its wings. So obviously the idea comes from nature, from flying insects, from hummingbirds. And we started as researchers who are just curious, can we build machines that can fly like that? But eventually we did that, yeah, we started a spin-off. We were at TU Delft at the time, and we were looking for commercial applications of these things.
Even the colors are beautiful, very elegant. And you mentioned hummingbird. They are very special, right? What's their main characteristic? They can hover, right?
Indeed. So hummingbird is the largest bird that can hover. Well, actually, it's one of the smallest birds, but it's the largest animal that can hover very precisely next to a flower. What is impressive, they can also fly very fast, do very agile maneuvers, and this is what we wanted to approach as researchers, as engineers who building such a machine.
Very, very interesting. And just to frame it within the context of our podcast, which is human-robot teaming, how do you see this robot as a companion, maybe, of humans?
Certainly. So, unlike propellers, flapping wing robots only have soft wings that move back and forth. So whenever you hit something, whether it's an object or a human, you just bounce off. So they are very, very safe. They are lightweight with soft wings. So we see them great around people. Great solution for flying robots around people. Whether it's for entertainment, they can do shows, drone shows where they fly in formations, in choreography with music. But it can also be in real-world applications where you just need a flying robot, for example, as a guide.
In a museum or
some
public space.
Certainly, yeah.
Really, really interesting. Well, we're just looking forward to see how it flies.
Let's give it a command to take off. And hopefully, there we go.
Very nice. It really
even pack
reminds.
It like this. It's not gonna crash.
There are sensors there on board.
There are sensors. There is a standard IMU for attitude stabilization. This one also has a sensor for the tracking system. It's the Lighthouse tracking system, low cost but very precise system based on VR base stations.
And when you get closer.
It doesn't have, this version doesn't have any proximity sensors, so it's unaware of its surroundings. But you can extend the platform with additional sensors, for example, time of flight sensors that go in any direction.
Very nice. So just out of curiosity, who is your ideal client?
Right now we're focusing mostly on universities and research institutes. This is a development platform, so people can program it. The firmware is open source. We use the CrazyFly Bolt as a flight controller, so people that work with CrazyFly drones can easily also start working with these. And in the long run, we're looking for applications where you want to fly, for example, in places where there's a lot of obstacles, like a greenhouse where you have plants you don't want to damage, but you want to get close to them. So that's one of the scenarios where a flapping wing drone could also be very good.
Very good. So thank you, Matěj, for the nice chat. And we are among us, they are among us for human-robot teaming. Thanks.
Okay, yeah, thank you.
Hello, everyone. Our friends from Among Us, human-robot teaming. We have a special guest today, Marco Agravi from Haption. He's a research and development engineering in this nice company that is based in France.
Yes.
And today we have a really exciting demo, which is very related to the topic of human-robot teaming, because we have a setup here with the teleoperation, with the haptic device.
Yes.
Marco could tell us a little bit more.
Right. So hello everybody. So yeah, what you see here is a typical teleoperation. So it's gonna be a classical Cartesian position teleoperation in which the haptic interface, that is the main product of my company, is gonna read the position of my hand basically and command around the position of the robot. So ideally we command the position of like here, so the palm of the hand.
Yeah.
Because we can put an haptic glove here and then have a hand-to-hand operation. But in this case, the glove is not available, so we will just command the hand of the hand without moving it.
So for our listeners, what are we doing here? We are connecting humans to machines.
Excellent.
So one-to-one, the movement of this haptic device is transferred to the machine.
So here the team is really the most simple one. So you have one human and one robot. Well, you can say two robots, but let's say he's part of me in this sense. And
it's an extension of the human.
It's an extension of me. I am augmented with this robot. That's actually what we do with our clients. We take the operator, we take the tool that they use, we put the tool on a robot, and we give them the control of that robot. So we augment basically the operator of a company with a robot. So
and it's not only one way, right?
It's not only one way. If now you push a bit the robot in that direction,
you will feel this force.
I feel this force. I can push. I can feel the interaction with the environment. So now I'm at the table that is stopping me from going down.
You're touching the table, so you're constrained by this.
I can feel, in fact, the force that the robot is applying or is receiving from the environment.
So this is. It looks very fluid motion and. How many degrees do you have here?
So here we have 6 degrees of freedom, so 6 motors.
6 motors.
We read the 6 position here, so translation and rotation, and we can actuate 6 forces, so three forces and 3 torque around that point here.
Very
it's
good.
An active haptic interface.
And what kind of applications? Is there any use cases that you? Nice
the original use case of our device was the nuclear industry, where you had a very big manipulator, which was controlled with basically the same robot put in the reverse direction. So you would do one-to-one motor control.
One-to-one, yeah.
What was the idea of my boss many years ago was to have an interface that was a bit more human-friendly. So they made the first iteration of this haptic interface. And then you will control a manipulator, a very big manipulator for the nuclear industry with a smaller manipulator with a force factor that will actually make you feel less or more, depends on the task, the force that the robot was applying on the environment.
So you can basically scale up and down.
But everything, so these 2 robots or any 2 robots that we control, they are connected to the same PC. And we know the data flux between the 2 of them, and we can control everything. So we can scale forces, we can scale position, velocities, or even constrain the robot on some axis. So what you call in the robotics, you can call them virtual fixtures. Or you can have avoidance with virtual walls, like bounding boxes and stuff like that. Or you can, for example, if you want to drill, you want always to drill straight, otherwise you break your tool. It happened to me recently when I was like drilling not really aligned with the hole, and the drill broke. with the robot, it would be even easier to do this movement because, especially if the robot is big.
It's like zooming in, right?
Yeah, you
It's
put
like
a virtual fixer, you force the robot to be in that direction,
that
and the
direction.
robot will go in and out in that direction, and you will have a perfect drilling. But to come back to the applications, so we have
Is
a
there
lot of
any
clients still in the nuclear industry.
example that you will noticeable example that you're
But the idea is that, as I was saying before, we augment the operator, or we reduce the physical fatigue of the operator. So, for example,
so this is very interesting for this concept of teaming, because we are delegating, shifting the workload to the machine.
you
right?
have a task, for example, we are really active at the moment in the foundry, so heavy metal production industry, where you have a piece, you produce a piece of metal, and then you have
Heavy
some,
and huge.
heavy and
part,
huge, and you have some imperfections, because not your process is not perfect. You have some imperfections that you have to clean by hand, and at that moment there is someone going there with a grinder, like fully suited with some special equipment done for the task,
Protective
and is
equipment.
doing the task by hand. We saw that there was a potential to help that operator. So we took the grinder, we put the grinder on the robot, and now the operator is using our robot to control the robot.
In a much more safe and also less fatigue.
And there is the important concept here is that we do not use robots to replace humans, but
Exactly.
we use robots to augment them, so to help them. So on a side, the operator still do the job that he was doing before. On the other side, the company still keeps the employee, because it has a social part. So you keep the person that was working for you, but you keep also the knowledge.
Very
That's
good.
really
So this is in line, by the way, with we have a song on our podcast,
Okay.
and part of the lyrics says, "We are stronger when we are teaming." And
It's really
just
good.
another small detail. I mean, I know Marco since many years. We have been studying at the University of Siena, so we have common friends, and it's always nice to catch up.
Yes.
And see the gradient of your projects and your work, and it's really nice to see how much in line we are from a scientific point of view, but also with a product, an application
with a
that
real
actually
product
it's
that
on the
is,
market.
yeah.
And yeah, so I'm really looking forward to see more of your projects. And the setup, would you tell us a little bit more about the hand itself? It looks like you have tactile sensors here.
Yeah, so the booth that you have here at ERF is actually a collaboration of many companies.
Many companies, yeah.
So there will be Aption with the haptic interface, Sense glove that is not here at the moment with a haptic glove.
That you can connect
that you
here.
Put it here,
Yeah.
yes. And then the only non-European companies at the moment is Kinova, so it's Canadian. They make these arms since many years. And then you have the hand from Seed Robotics. This is a company from Portugal.
Portugal, yeah.
And so let's
And
focus on
the
the
hand itself is sensorized.
It's sensorized. They make the robotic hand plus the force sensor, so you can either buy the force sensor alone or you buy the robotic hand. And ideally, you have, if I understood correctly, you have 6 motors. So you have this kind of movement plus 1 motor per finger.
So it's
They
under
just close
actuated,
it.
the
It's
hand.
it's highly under actuated, I
Yeah.
would say. The idea is just to close the hand. And you have the force sensor. If you go to their booth, you can also try the force sensors alone, because
Yes.
they also sell the force sensors alone, which are quite fine. They're fine, they're soft. I mean, they're maybe not the most precise one, but they can, the way they made them, they can be used in a rough environment. They can be smashed. They don't break.
So they're very
that's
robust.
important. Yeah.
Yeah.
You can
So
get an
then-
industrial grade force sensor, but then you smash it once and it's broken.
Yeah, for
more-
our listeners, this gives tactile sensing to the robot, and tactile sensing is one of the strongest sense that humans have. So we are basically able to do grasping and manipulation thanks to this sensorization. So it's very nice to see also the cross collaboration between companies,
Yeah.
and that you are open to to have synergies with.
It's a really
it's a
important
win-win
point,
to everyone, right? For everyone.
So it's interesting to see how manipulation, that was a buzzword many years ago, was a bit forgotten for many years. Then now with the arrival of humanoids,
Embodied AI and so on.
embodied AI, now manipulation is again a very strong research field, and there are a lot of companies that are producing robotic hands. There is a colleague of us here that has a website where you can see that they do reviews of robotic equipment, and if you filter by hand, you can see there are around 27 companies now that are producing robotic hands.
So that's really nice to see this.
The highest, the whole time highest, because
this
27
momentum.
different hands of full forms, like all anthropomorphic, but like from this size to this size. And that's really cool to see that robotic manipulation is back into the market. Very strong.
Really nice. So, yeah, to see this momentum that starts from LLMs and the trends that we are seeing with AI and so on. It's really nice to see how robotics is filling up this gap.
Yep.
And I think with this, I would like to thank you, Marco, for a nice discussion with you.
Yep,
and would you like to say a few words to our listeners? Anything about human-robot teaming? What do you see the bottleneck of this kind of concept? Is it manipulation, maybe?
So it really depends if you want to go to teleoperation or autonomy.
Autonomous,
So
yeah?
teleoperation,
For example, this is teleoperation, where
teleoperation
autonomy
is basically done.
Yeah.
So you can teleoperate, for example, a humanoid arm and hands to do a task. But then if you want to go into autonomy, there is still a lot to be done.
Yeah,
That's where
exactly.
NVIDIA and all the physical AI are into play. But like for a teleoperation point of view, we are really close to have a full product.
Very good. Thank you, Marco.
Thank you. Bye.
Okay, a few moments later, we actually connected the glove to the haptic device. This is a glove that SenseGlove has developed, and we have Akshay here showing us this demo, and Pierre, who is the CTO of the company. CCO of the company. And this is a really exciting example of human-robot teaming. We have the human on one side and the machine on the other side. Pierre, how did this device came into reality?
Well, that would be more question for Akshay, but I can answer it. Well, for the last 2 years, basically, we've been developing since 2017, actually, haptic devices. We consider ourselves hapticians. We've been developing four generations of gloves.
Four generations.
Four generations.
Nice.
Yes. So this is the fourth. And initially, we developed 3 gloves between 2017 and 2024 that were using passive force feedback systems with magnetic brakes, including actually the first glove we made was actually also an exoskeleton, but also passive force feedback system. And we wanted to bring human touch to first the virtual reality sector, so more intuitive ways of interacting with objects in a virtual reality environment, and that then has poured out sort of indirectly and then by design into the robotics industry. And so for the last couple of years, we've been developing an active force feedback glove that was to answer this strong demand for human touch interaction for teleoperations, for imitation learning. And so what we developed here is a 20 degrees of freedom, we're on recording, 20 degrees of freedom glove with 35 sensors in the tracking the movements of the fingers. We have four fingers with active force feedback, and with between the measuring from 10 grams to about 2.5 kilos per finger, and then vibro-tactile in 4 fingers in the hand and 3 points in the palm. So
even the palm is
yes, we have vibro touch. So that's, for instance, when you have a sense of rubbing or touching the surface or contact. And then this means that the operator will have a way more intuitive and natural way of interacting with the machine or getting feedback from the glove and getting the signals and the cues of touch in a way that is actually way more, yes, intuitive, as I said.
Very good. So
Yeah.
for our listeners here, what we are seeing is Akshay can actually feel what he's touching, right?
Yes.
He's growing a grasp this small bottle, and he's feeling the weight, feeling the contacts.
Yes, so actually the weight is actually, so this is coming from our collaboration with Haption. So the weight part is going to be, and the resistance is coming from the Kinova data transmitted to the Haption. So if I pull his arm here, he will feel that, that pull. And then for the hand feedback, this is coming between the data from the hand is going directly to the glove. So we have these sensors on this hand where basically if I pull his fingers, he will be feeling that here, and depending on the stiffness of objects, these sensors transmit that data and then he feels it directly.
So there is a bilateral connection between the machine and the human.
Yeah.
So this is very much in line with the concept of human-robot teaming, even though here the levels of autonomy are really low. Everything is, the human is in charge in this case,
In
right?
this case, in this teleoperation setup, yes. But it is also...
It's possible theoretically to shift some of the, for example, the decisions later to the robot at some point.
I mean, when we're you know, everyone's talking about physical AI now, and this is a glove that's been designed for, you know, two purposes, human teleoperation and physical AI. So basically training these hands to be autonomous, you know, first through an operator and then independently, so that the robot has a precise tactile approach to the interactions he has to perform.
Very good. And by the way, for our listeners, you see the fun of live recording. We are in the middle of the expo here in Stavanger for the European Robotics Forum, and it's really exciting to see how technology is progressing into real life. This is a commercial product, so it's nice to see the bridge from science into the market.
Yeah, no, absolutely. Like the human-centric design is, I think, very important when we're designing technologies, especially for dexterous manipulation, because you know it is the most natural interaction you can have via robots, and of course, you know, robots are in a way mirroring ourselves for certain tasks, and in the future will even more, and especially in the humanoid industry. So, no, we're very excited about this and what it's going to bring to the market.
Yeah, very modern looking, even the design looks modern. And thank you guys for a really nice demo. We look forward to see your next projects.
Well,
thank
you're
you
going
so
to see
much.
a lot about us, so hope we'll make us some buzz and you'll see us everywhere. Thank you.
Thank you, Akshay.
Handshake.
That's cool. Great. I think we have everything. Thank you for the nice introduction. I'm actually here on behalf of one of our PhD students, Evan Langas, and this is a teamwork together with Norse, Atle, and also our chair here, Daniel, and myself. So we are actually following up on this idea of human-robot teaming, and the title of this work is Transformer-Based Human Trajectory Prediction in Manufacturing Settings. So when we have machines and robots working so closely to each other, we imagine that the two main actors in this kind of collaboration need to share space, physical space, they need to share decisions, they share forces. And in such a close collaboration, proximity and vicinity, we imagine that the machines need to predict the trajectory of humans so that we can dynamically adapt the production without stopping the machine, without stopping the robot, avoiding collisions, but still adapting the production. So this is the main idea behind, and by the way, about this topic of human-robot teaming that we are trying to formalize with the help of many researchers, we have a podcast, and if you like to scan the QR code, you can get access through Spotify or all the other platforms. So this idea of teaming is a progression that starts from many years ago, where we had robots in a cage, completely separated by humans, because there most of the tasks could be completely automated. But today we have several tasks where we can't, humans or neither robots can achieve this task by themselves, they need to team up. So that's why we are defining this concept, and we believe that for this we need help from several fields. For example, in this section before there was a presentation about emotions. In such a kind of concept, emotions are very relevant. We need to know if the person is under stress. We need to adapt the machine to that kind of emotion. So let's dig into the scope of this work. So why do we want to predict trajectory? We want to do this so that if we want to make an analogy with self-driven cars, for example, if you have been on a Tesla, you have the screen there and you can actually have a taste of what we are going to do here. You can see your own car, you can see the other cars around, maybe pedestrians, and you see maybe an arrow showing where the car is heading, right, in real time. So imagine the same idea applied to an industrial context where you have workers and you want to predict where they are heading. You have different stations with robots, and you want to predict where the people are heading, so that you can perhaps, if you have a robotic arm here, you can slow it down, or you can make it work on the other side so that the person is safely going past through. So this is the why of this work, and it's been a progressive work that we have done. So we started with a simulated environment, and we applied some statistical models where we generated these trajectories there. These blue trajectories are people walking in this work environment. So we have 5 workstations, and there are operators working from one station to another. Maybe I have this part here, it's been machined, and I want to take it to the other station for painting it. So we use some statistical models to generate all these blue trajectories, simulating the locomotion gait of operators. And then we have applied some machine learning so that we can predict at a certain point ahead of time, like 10 seconds before, 5 seconds before, 3 seconds before, where the simulated operator is going. So this was some preliminary work. And then finally, thanks to the collaboration with Norse, we have applied it to a real use case. And as a sensor, we used a modified LiDAR that you can actually see down here at the hood with Norse. It's actually operating in live. So we placed that LiDAR on the ceiling of this workplace, and we have these 4 stations, and then we have people with a defined task, operators, walking from one station to another. So based on this real set of data, we have applied our predicting models. So this is how the data set looks like. We have an indoor industrial area that is 26 meters by 20. We have captured this data from a roof-mounted LiDAR, 6 predefined workstations, and volunteers have walked for 20 minutes each. We have randomized this, so it's dice-based transition. So each user was required to shuffle some dice, and it was given some specific stations to order of stations to follow. And then we have generated this data set with 487 separate trajectories with randomly selected start goals pairs. So here, that's how the entire data set looks like. And this is the modified LiDAR. It's very interesting actually, because we have added a set of reflected mirrors. In this way, you can actually, on one side, you reduce the view of the LiDAR, but at the same time you increase the resolution because you have reflected beams. So in the center part of the field of view, you have much higher resolution. You can track even steps, and according to the height, you could even track finger motion. So it's a very interesting application of this modified sensor. So here is the data processing part. So we have shuffle trajectories before the train test split to avoid ordering bias. We have a slide window. This is important because these are temporal data. So we have a past window, the future target, and the step size equal to 3. And then we have normalized across coordinates and split into 80-20, conventional way of doing the test. And here is the model itself. So we have a dense layer set of steps with 2D coordinates. We have a sinusoidal positional encoding, and then 3 transformers blocks. And a time distributed dense layer that maps the representation back to 30 feature. And then we have decided to use some state-of-the-art baselines like temporal convolutional network, GRU, and LSTM. And as a loss function, we are using the mean square error, and matrix the standard R square, MAA, relative MAE, and MSE. So these are the parameters that we have selected. Of course, you are very welcome to read the details into our paper. And here are our results. So basically, as you can see on this table, we have compared our model with DCM, GRU, and LSTM, and according to 4 different metrics, we can see that R square, of course, bigger numbers are better. In this case, smaller numbers are better. And we have also tried to visualize this into these nice plots. And probably these ones are the most interesting, where you see the input. The green line is the history, where the person has been walking so far. Then the orange, the yellow line is the ground truth, and the red is the prediction. And you can see how our transformer-based model performs there compared to the competing models. So we can look at the performance also by looking at this plot here, which is very interesting. It's actually very counterintuitive. As you can see, this is our prediction horizon in seconds, and this is our mean absolute error. And if you see, our model is the yellow one. So when the operator is far from the workstation, the prediction is much better than the competing models. But as soon as we approach and we get close to the workstation, the other models start to actually perform very closely to our model, and this is expected because of the way how the transformer model works. And as a future work, we are considering to add robots in the workstation, mobile robots. So we will not only have, in this first study, we had fixed workstations and moving people. Here we will have also moving robots. So we are going to also track the movements of the robots, as in a proper industrial scenario. And with this, I would like to conclude, and I'll be very happy to answer your questions.
Thank you for presenting this slide where you showed the timeline?
The results?
Yeah, the results. Sorry. Yeah, I just want. Would you mind talking us through that a bit more?
Please.
So
yes, the yellow-orange line is our model, and as you can see here, the error is much lower than the competing models when the person is far from the workstation. So it's a very good prediction. For example, 5 seconds before I reach the station, right?
yes.
But when I get closer, the other models are catching up.
Why is yours getting worse?
That's a good point. The point is that when we get closer, our transformer model is at least not better than the other models. So it's not. It looks like it's getting worse, but it's actually still better than the other models.
Through the noise of doubt and distance, through the fear of what may be, we found trust in every motion, in shared autonomy. Not replacement, not surrender, but a fusion of design. Intelligence extended, your decision joined with mine. Oh, we rise together in the space where futures start. Oh, not rivals, partners, code and courage, mind and heart. Among us, stronger when we're teaming, human hearts and circuits dreaming. Side by side we stand. Among us, shared control, shared believing, human robot teaming, shaping what we are. Is it systems